So once you've determined that you have a problem that actually can be solved using separation of variables, so it fulfills all those requirements, then step 2 is you go through the process of separating the variables. And what that really means is you're going to take this this temperature solution, which is a function of x and y, and you're going to assume that it can be expressed as the product of a function tx, which is only a function of x, and another function ty, which is only a function of y. So you're basically trying to separate the x dependence and the y dependence out, right? That's why it's called separation of variables. So you take this idea and you substitute it into your math problem, and the outcome should be that you end up with 2 ordinary differential equations, right? The product of their solutions will give you the solution to the partial differential equation, right? That's the idea. We know how to solve ordinary differential equations. You know, we use that knowledge to solve partial differential equations. So that's what we've done here. I'm making this assumption, and then I'm just going to go with it, right? So I substitute this into here. I have the second derivative of t with respect to x, and I have the second derivative of t with respect to y. So for t here, I put tx times ty, and for t here, I put tx times ty. Let me get my pen. Yeah. So if you think about what's going on inside of here, this is a function of x, but this is not, right? So if it's not a function of x, I can actually pull it out of the derivative, right? Because its derivative with respect to x is just going to be 0. So that's what I did here. I pulled it out of the derivative, and then I have 2 derivatives of tx with respect to x, and that's what I have here, right? And actually the other nice thing you can see is that these partials became ordinary derivatives because tx is only a function of x. So this becomes ty times d squared tx dx squared. Same thing here. In this case, tx is not a function of y, so I pull it out, and I'm left with tx times d squared ty dy squared, right? So that's progress. The next thing I do is I'm going to take this whole big thing, this mess here, and I'm going to divide it by the product of tx times ty, right? So that's what I did here. I divided by tx times ty. And what you can see then is for this first term, the ty terms cancel out, and I'm left with this. And for the second term, the tx terms cancel out, and I'm left with this, right? So what I've done here is I've shown that if I make this substitution, I end up with something that's only a function of x, right? Everything in here is only a function of x, plus something that's only a function of y has to equal 0, right? So let's think about what that means for these 2 functions. So if you think about the fact that this expression here has to be satisfied everywhere inside of this computational domain, right? So no matter what value of x and no matter what value of y I choose, I have to have this be true. You should be able to convince yourself that the only way that can possibly work is if both of these 2 functions are actually equal to constants, right? So it's pretty obvious that whatever I have here has to be equal to negative whatever I have here, right? That just means that when I add them up I get 0. That's easy. The little bit more tricky part is the fact that they both have to just be equal to a constant. So why is that? So let's think about if I were to move along a line of constant y, right? So I'm moving here in the x direction along a line of constant y. What would happen if f sub x was not equal to a constant? Well, as I move along this line, f sub x might change, right? F sub x could be changing. So this part of this could be changing. But as I move along this along this line, the y value is not changing, so that part of it over here can't change, right? So there's no way that I can let the f of x change if I can't let the f of y change, right? So the only way I'm going to make this work, again, is if both this group and this group are constant. And of course, then they have to be equal and opposite constants. So that's what I've done here, right? I've said that this guy here, f of x, is just a constant, right? It's going to be, we're going to call it lambda squared. Again, we use the squared here to make it clear that lambda squared is positive, and I can either have a positive or a negative constant that works. And then I'm going to take this other group, f sub y, and I'm going to say that it has to be equal to the same constant, lambda squared. Except, it's really important that if I pick the positive constant here, I got to pick the negative constant for f sub y. If I pick the negative constant for f sub x, I got to pick the positive constant for f sub y, right? They both are constant, but they still have to cancel each other out. So here's the same equations, right? F sub x, and it's this group here, is equal to either a positive or a negative constant. F sub y is this group here, equal to either a negative or a positive constant. If I just bring the tx up to here, I get this. Let me get my pen here. So I get this here. And then if I bring this to the other side of the equal sign, I get this here, right? Same thing here. If I bring the ty up to here, I get this. And then if I bring this whole thing to the other side of the equal side, I get this right here. So what have I done? I've gotten myself to the point where I have two ODEs, right? I have d squared tx dx squared is either minus lambda squared tx or plus lambda squared tx. And then d squared ty dy squared is either plus plus lambda squared ty is equal to 0 or minus lambda squared ty is equal to 0. I don't think I said that quite right, but hopefully you get the idea, right? I have two ODEs. They only differ on whether this last term is negative or positive, right? So I actually have a choice here. I can choose a negative sign here and a positive sign here. I can choose a positive sign here and a negative sign here. And it's important that you make the right choice. At this point, it seems like it's going to work no matter which choice you make. But it turns out that looking ahead, you have to make the right choice. And the right choice is related again to which direction is your homogeneous direction, right? So if we go back and think about the requirements that we were talking about for separation of variables, one of the requirements was that both boundary conditions in one direction must be homogeneous. And we said that we had that here, and that direction was x. So x for us is our homogeneous direction, right? Obviously in some problems it might be y, but in this case it's x. So when I get to this point here, I have to recognize that my x direction is the homogeneous direction, and therefore when I solve my x direction problem, I'm going to end up getting very special functions that are called eigenfunctions, right? This x direction problem is our what we call our eigen problem, right? So that guides what choice we make here and what choice we make here, right? Our homogeneous direction must provide our eigenfunctions, and our eigenfunctions are always going to be sines and cosines, or the combination of the two. So if I go back and look at my sheet in terms of what ODE gives me sines and cosines, it's going to tell me that the ODE that's solved by sines and cosines is the one that has a plus here. The ODE that's solved by sinches and coshes is the one that has the negative here, right? So if I have to get sines and cosines in the x direction, I better choose a plus, right? And then whatever I choose in the other direction has to be the opposite, which is a negative. Hopefully that makes sense. But anyway, that's the choice that you have to make. And again, you know, you're not allowed to make it arbitrarily. You have to make it based on this idea that one of your two directions is the homogeneous direction, and in that direction you're going to get what we call the eigen problem, right? So here's our eigen problem. Okay, so that is step 3. Actually, step 3 is solve the eigen problem, right? You've split your problem up into two ordinary differential equations. Hopefully these ordinary differential equations look a lot more friendly to you than the partial differential equation did. We've solved ordinary differential equations now for a little while, so I know how to solve these two guys. I got to focus on this one first. That's our eigen problem. So solve the eigen problem. That's not hard. This is solved by sine and cosine, right? So if you look on your sheet, or if you ask Maple, or hopefully after a while you'll just remember that this particular ODE is solved by some constant times the sine of lambda x plus some other constant times the cosine of lambda x, right? I need to get C1 and C2, which means I need some boundary conditions. So where am I going to get boundary conditions for this differential equation? Well, I get them from the original problem. And not only that, if I'm talking about this x direction solution, I'm going to get them from my homogeneous boundary conditions in the x direction. So at x equals 0 and at x equals w. So the homogeneous boundary condition at x equals 0 is that the temperature has to equal 0. So if I plug in this idea that temperature is Tx times Ty, that's going to tell me that Tx at x equals 0 times Ty is equal to 0. So I can make this work in two ways, right? I can make this work by saying, well, let's set Ty equal to 0. But if I set Ty equal to 0, I basically just set T equal to 0 everywhere, and that's not going to be useful. So the other way I can make it work is say, well, let's set Tx at x equals 0 equal to 0. And that is the first boundary condition for this general solution. And then we do the same thing at the other edge of the boundary, so at x equal w. At x equal w, we said dt dx at x equal w has to be equal to 0. Again, let's substitute this assumed form of our temperature distribution into here. So if I do that, then dt dx is going to be equal to Ty times dt dx. This should be dtx, sorry. dtx dx at x equal w. And again, Ty can't be equal to 0, so dtx dx at x equal w has to be equal to 0. So this is my other boundary condition for this general solution. So here's my two boundary conditions. Here's my general solution. We're just going to do some substitution the way we've done a few times before. So I take this general solution, I'll plug it into, let's do the first boundary condition at x equals 0. So Tx at x equals 0 is C1 times the sine of 0 plus C2 times the cosine of 0. The sine of 0 is 0, the cosine of 0 is 1. So this says that C2 is equal to 0. Right? So this term here goes away, and I'm left with Tx then is just equal to C1 times the sine of lambda x. Right? And if you think about it, yeah, every sine is going to be equal to 0 at x equals 0. So that every sine is going to satisfy that boundary condition. We call the outcome of this first step the eigenfunction. So this is my eigenfunction, right? That'll be a little clearer when we move forward, but just so that you know what I'm talking about when I say it later on, you know, these are the solutions in the x direction are called eigenfunctions. And in this particular case, my eigenfunction is just sine of lambda x. All right, so we have one more boundary condition to apply, which is this other one over at x equals w. So let's see. I'm going to take the derivative of this thing at x equals w. I get C1 times lambda times the cosine of lambda w has to be equal to 0. So I can make this work in a bunch of different ways, but again, really only one way is going to be of any use. I could say C1 is equal to 0, but if I do that, I've just said that Tx is equal to 0, which again gives me just 0 everywhere, so that's not a useful solution. I could say lambda is equal to 0, but sine of 0 is 0, so I've just done the same thing, not a useful solution. But the last thing I can do that actually is kind of useful is I could say, well, the cosine of lambda w needs to be equal to 0. And that certainly is something that I can make happen. That's called our eigencondition, right? So the other thing we get out of solving the eigenproblem is our eigencondition. Our eigencondition is always going to give us not just one solution actually, but a whole bunch of solutions. So if you think about it, the cosine of lambda w equals 0, that's going to be true when lambda w is pi over 2, but then it's going to be true again when lambda w is 3 pi over 2, and then 5 pi over 2, and then 7 pi over 2, and so on forever, right? So there's not just one value of lambda that satisfies this eigencondition. There's actually an infinite number of them, and that's always going to be the case. We find an eigencondition, and that eigencondition is going to have an infinite number of solutions that we call eigenvalues, right? So these lambdas, these are our eigenvalues. So for this particular case, our eigenvalues are given by this formula here. Lambda I, so there's a whole bunch of them. I need to number them, so I'll number them with a subscript I, is equal to 2i minus 1 times pi over 2w, where I is an integer 1, 2, 3, all the way up to infinity. So if I plug in I equal 1 here, I get, 2 minus 1 is 1. I get pi over 2 to the first one. If I plug in 2 here, I get 3 pi over 2, and so on and so forth, right? So that should be the outcome of solving the eigen problem. Is you should end up with your eigenfunctions, which are our signs, and our eigenvalues, which are going to be the roots of some eigen condition, right? Okay, so we're making good progress, I guess. The next step then is you have to go back and solve the ODE that you got in the other direction, right? So we solved the eigen problem. The eigen problem was the problem that we had in the x direction. Well, we had another problem in the y direction, right? We solved this x direction problem, got this solution. What is our y direction problem? It was this other ODE, and we need to solve it. But actually, before you do that, you have to recognize that we don't just have one of these problems, we have a whole bunch of them, right? We came up here and we found that this problem here is solved by a whole bunch of eigenfunctions, each having their own eigenvalue, right? So if I come down here and look at this, every lambda I is going to be related to one of these ODEs that will have a solution TYI. In other words, there's going to be a whole bunch of matching problems, if that makes sense. So I have to solve this non-homogeneous problem for every eigenvalue. Right? So this is my problem that I get for each of these eigenvalues. Right? I get this ODE here. This ODE is not difficult to solve. You know, again, if I don't just instantly recognize it, I can go to that sheet and look in the sheet, and it says that this is solved by Kosh and Cinch. Or I could just ask Maple, what's the solution? And it would happily tell me Kosh and Cinch. So there's my solution to this part of the ODE.